because I want to see what the path of a point that initially started down at the bottom, what path does that follow as the wheel continues to roll? So here's our wheel rolling down the road. Here's a spoke. Here's our point that we were interested in. When this wheel has rolled some amount, then let's say it's moved over here. The center of the wheel is moved from here to here. Now the spoke is, the wheel has gone through some rotation. So our spoke is now pointing something like this. So P is moved to here. P prime. The wheel has physically rotated through this angle, hasn't it? And what's happened is a piece of the tread, now going down to the ground, there's a new portion of this tread which happened to have been back over here. This point gets laid down onto the ground, doesn't it? Okay. So here is an arc length of tread that is laid down on the ground. That arc length of tread has now gotten laid down on the ground. And that arc length is our theta. R theta. Right? And the speed, the rate of change of that S is what? R theta dot. R omega. And so that's the speed that's going on here. R theta dot, which is R omega. And I explained that to you in another way before I erased it as fixed axis rotation. Okay. I want to know the physical position of P prime. Physical position of P prime. So let's set up an axis system. Here's Y, and let's say down the road is X. X and Y. So I want to know the X coordinate of this point. Well, I just keep track of the center of the wheel. So it's distance S over, and then I have to back up this portion of this triangle right here. Careful. That's opposite theta, isn't it? Sine, opposite. So, and here's your R. My drawing's reasonable. So we're going to go, X is then going to be equal to S, which is R theta, minus R sine theta. That's the geometric relationship between X and theta. See it or not? Everybody see it? Joel? I come over to here, which gets me to the here. This wheel is moved forward distance S, and then I back up that distance so that this is my X reading right there. Everybody got it? Okay. Do the same thing for Y. How high up is this point? Go up to R and back off R cosine theta. Go up R and back off R cosine theta. So Y is equal to R minus R cosine theta. I don't like to use this colored marker because it doesn't erase well, but I want to plot this path. So for this point P to end up at the top of the wheel, how far down the road do you have to go for the point P to end up on the top? 1/2 of the circumference, right? So I have to come down the road. Half of 2 pi r is pi r. I have to come down the road pi r distance for P to be up here at the top. To get that point P back down on the surface again so it can pick up some more rainwater, we've got to get through the entire circumference, 2 pi r, for it to come back down on the ground. The path looks like that. And then it picks up and continues on again. Is that a parabola?
You might want to solve y for theta and plug that into x just to see exactly what it is, but it's so symmetric, nice.
I'm going to send Alfred home to solve that for me.
No, you solve the theta and y, not the other one.
Okay. And then plot them in here.
Yeah.
Okay. This is a cycloidal path. It's not parabolic. What's the shape of the curve right here as it comes into the ground here?
It comes in normal to the surface.
Comes in vertical. Comes in vertical. Slows down, doesn't it?
It has to if it's going to stop.
Yeah, if it's going to come down and stop and then lift back off again, right? So it's got to have all those different mechanisms of dynamics in it to, and the velocity on the blue path here is what direction to the path? The velocity.
Velocity of the particle P is always going to be along.
Always tangent to that path, is it not? And here its speed is 2r omega, like we mentioned, like we determined earlier. And when the particle is halfway up, it's heading down here at what speed? We did that earlier.
Wasn't that root?
It'd be the same as its speed over here, wouldn't it? At that spot? Square root of 2r omega. See that? Where is its normal acceleration greatest?
Where its velocity is greatest because it's moving along the edge of the wheel. So top of the path.
Let's see.
Probably right where it turns around. Or the
R omega, think about it. Isn't it r omega squared? If you have, well, but think of r as generalized r.
So ours, the car's racing.
Yeah, because the fixed axis it's momentarily rotating about is down here, isn't it? Always down here. So that's going to be the biggest value, isn't it? Up here at the top, and it's pointing downward, isn't it? Okay, so this is going to be the speed up here at the top. Its normal acceleration should be what? What should it be?
These are negative. You're doing
4r squared omega squared over 2r. So you could cancel one.
What were you thinking of when you just started saying that?
V squared over r.
V squared over r?
Yeah.
Or why don't you think r omega squared?
Sure.
What's the effective r?
2 times the radius of the wheel.
2 times the radius of the wheel, right? Because of momentary fixed axis rotation. So it should be 2r omega squared, shouldn't it? Right there. Okay, so how do we check those things out? because I've been telling stories so far. Well, get on the rolling wheel. Get on the rolling wheel, right? Okay. Well, look down here. We got the geometry. Let's crank out derivatives. See what we got. X dot equals r omega minus r cosine theta dot. Doesn't that give us an omega tucked in here? Let's not do acceleration yet. Let's go over here. Y dot. Constant. Derivative of cosine minus sine makes this positive. R omega sine theta. Because don't forget you're differentiating using chain rule there. Okay. Let's go ahead and get the accelerations while we're at it. X double dot, R alpha minus R alpha cos theta. Now that's a product rule going on here. Everybody with me? Product rule. So we did the derivative of the first. Now we need to take the derivative of the second, which is
Plus R
minus sign becomes plus R omega with another omega showing up, sine theta. And oftentimes this term is written in a factored form where you pull out this R alpha, 1 minus cosine theta, just makes life sometimes a little simpler for you. Feel good? Where is the hard part in doing absolute motion analysis from this simple example? The hard part is right here. That's the hard part, as I mentioned earlier. Okay, let's go ahead and get the y double dot since we're at it. R alpha sine theta plus R omega squared cosine theta.
Okay.
So,
What if the wheel isn't round? I don't expect to go through the derivation, but
oh, I'm going to get to that. We're going to have fun. Okay, what if the wheel is not round? Okay, we'll get to it. Okay, I want to stick with something that we can handle for a moment. Okay, now let's check what we just talked about here at the top of the wheel. What's theta? How much rotation has occurred?
pi.
Pi. Okay, so theta up here at the top, theta equals pi. Let's come down and look at our velocities. If theta is pi, cosine of pi is -1, so this becomes positive and you end up with 2r omega. Pretty slick. Let's check out the acceleration. Let's look at the x double dot up at the top of the wheel, putting pi in here. -1 becomes positive and you get 2r alpha, and at pi this zeroes out. So we get 2r alpha. So up here we have an x double dot term at the top equals 2r alpha. That should be consistent with what we talked about earlier. Okay, the tangential acceleration will behave similarly to what the what the velocities were doing. Okay, what about y double dot at pi?
That'll be 0.
Zeros out.
That'll be
Negative r omega squared. Oh. Negative r omega squared here.
Yeah, but the coefficient's
Well,
wrong
downward is
too.
fine. Negative is good. But we were conjecturing a doubling on that radius there, but it's not. It's r omega squared.
We were thinking the effective radius of rotation being
Yeah.
the floor.
The accelerations, the velocities behave the way I was describing earlier, but the accelerations do not. Okay. There's a reason for that. Okay, so that's how you handle a cycloidal motion. Now, we have a few minutes left. I think I'm going to give you a handout on the cycloid. I'll give it to you next class session. But I think what I'd like to do is we have enough time to actually do another problem real quickly, another one where we come up with the geometry, and we'd be done in less than 10 minutes. Okay. There are all kinds of applications. Before I go on, what if I put like a planetary gear inside here where we have an arm that hooks here, and we give this some omega, that rod, and then this wheel's going to roll inside that, right? So what's going to happen is this thing is going to form a cycloidal path. Something like that. Okay? A cycloidal path inside a circular surface. You can do these inside, as you were mentioning, non-circular. You can do these kind of things inside elliptical shapes or other types of shapes as well. And all you got to do is work up the geometry, and I'll show you a project that some students a few years ago did here in lieu of an assigned essay. Okay, let's grab another problem though, just so I can help you with the geometry here. Why don't we see if, here we go, this one, you have a mechanism right here. Here's a piston kind of mechanism, and we have defined x right here, and what we were looking for is the angular velocity of link AB, this connecting rod right here, AB. And what they gave us, point A is given a constant acceleration A to the right. So we have this rod here moving to the right with acceleration equal to A constant. And what we're interested in is the omega of member AB. The lengths of the crank arm and the connecting rod are B, and this is distance described x in the problem from a non-moving reference point. Feel good? So we need a geometric relationship that we can then tie into this given acceleration to help us determine the angular velocity of this member. So something from the geometry that we can observe here is that this triangle remains isosceles. triangle remains isosceles, which makes the problem a little simpler for us. So we can define, and notice how I put arrows on it to define the sense of what's considered to be positive. So I think you can see, because of the isosceles character, the distance x is made up of twice b cosine theta. Feel good? Okay. So we start taking derivatives here, and we get that x dot is minus 2b omega sine theta, and then x double dot equals minus 2b alpha sine theta. Okay, hang on a second. Minus 2b omega squared cosine theta. Question?
In order to have an angular velocity, we need to have it around some axis.
Uh-huh.
Where's our given axis? Given axis in the
I
problem?
have a fixed axis along here. Even though that point is moving, this bar is always rotating about a point on that axis.
Okay, so the axis is moving around, and we are looking at rotation of that point of B.
Wouldn't B
When-
be changing as well?
Excuse me?
Wouldn't B change as well?
No, B's not. B's inextensible. This is their crank.
The B up top is.
Yeah, and little b is fixed. Okay. So, what did they give us any other information in the wording of the question?
Starts at rest.
Starts at rest.
With x essentially 0.
Excuse me, with x
says-
essentially 0.
Yeah.
Okay.
So all the way in.
Okay. And then they're looking for an expression that describes the angular velocity of that member. So the angular velocity of that member is going to be right here, isn't it? Right here in this equation. So if we solve that, well, actually, we have to go down here, it looks like, doesn't. Okay. Okay. Starts from rest with a constant angular acceleration. Ah. Okay. Oh, I'm sorry, a constant linear acceleration. So this is fixed. I was looking, it looked to me like there was one too many unknowns in here. Do you see what I was looking at? I was looking at this thing having an alpha in here, a different thetas, omega. So it looked to me like we had too many items in here. So let's just take a moment and see if we can get somewhere with this. This is A, isn't it? Okay. So we have then that the negative of A, I'm going to go ahead and pull the 2 over, has to be equal to then the positive B alpha sine theta plus B omega square cos theta. Is there some way we can get theta out of our equation? How can we get theta? Look at the geometry. How can we get theta out of our equation? Excuse me? Maybe something simpler, I'm thinking. I don't think we need to parameterize it. Well, we want to get theta out of there. I think what you meant by it is in terms of x then, right? Yeah, okay, that's fine. Can we do that?
Cosines, law of sines, both of them.
Okay. So we have a parameterization right here. So what we could do is we could draw a triangle showing theta whose cosine is x over twice b. So adjacent over hypotenuse, which would leave a square root of 4b squared minus x squared on that. And so then we could have some relationships related to sine and our described cosine. Is that going to help us get it? Does it?
Yeah, it should. Then you can do sine and cosine.
But what about the alpha? I guess alpha's got to hang in there. Well, I mean, they did tell us that A was constant. If A is constant, does that lock in anything about alpha? Think about the physical nature of this. If the acceleration is constant, does that lock in anything about the rotational accelerations of these members? Okay, let's just keep that in the back of your mind for the future. So, I think what I'm going to do in the interest of time is just stop right here. If you folks have that written down, these relationships written down, you might want to ponder that a little bit. And what we'll do is we'll pick up the next class session. We'll pick up on this, and that'll be this Thursday. Okay. So we'll just leave it at that. That's it for today.